So for carbon, we know we're going to end at 2p2, right? So I would just, I know the order in my head, so I know it goes 1s, 2s, 2p. So I know these have to be full, so I can go 1s2, 2s2, 2p2. So I don't really have to stop and think until I get to that last one and say, how many are in this 2p? There's 2. Let's write the electron configuration for phosphorus. So what is the symbol for phosphorus? P. D. So somebody will, first of all, where is phosphorus? Phosphorus is here. Okay? What's the first one? 1s what? 2. Then? 2s2. 2p6. It's full. We're beyond the 2p's. So there are 6 in the 2p's. Then what? 3s2. Then 3p. How many? 2. 3. I hear 2 and 3. Why is it 3? Right. 1, 2, 3. So there are 3p3. And that's it. You're done. That's 100% on the quiz. Just like that.
But you can write it either way, right? Like that or with boxes?
The question will specify. That's why I'm saying you have to remember which one is which. Okay? On a quiz, I am likely to say, draw the orbital diagram of manganese, in parentheses, hint, the orbital diagram is one of the boxes. Okay? That's not going to be on the final exam. Okay?
But the periodic table will be.
Wow. I seriously didn't know manganese was the next one up here. Okay. So we want to write the electron configuration for manganese. So I'm going to erase the P and put manganese. Okay? Manganese is here, which is past phosphorus, right? So I'm going to save myself some work and leave all this. But what do I have to do with this 3p3? Make it a 6. What is next after 3p6? 4s, how many? 2, and then 3d. 3d 5. I don't care if you do capital or lowercase. It doesn't matter to me. Yeah.
So a way for us to check it is we can just add the 2, 2, 6,
Yep.
2, and just make sure it comes up to whatever
Right.
the atomic
So
number is.
manganese has 25. If you add all of these up, that better come to 25. If it doesn't, something's wrong. That's a very good way of doing it. Make sense?
So this one's on the quiz, not the other one?
I haven't made the quiz yet. I just remember on the an exam last year, I actually did the hint, the orbital diagram is the one with the boxes. And then for the other one, I said hint, electron configuration is the one without the boxes. Okay, we're not necessarily going to do all. Okay, so let's do, somebody pick one. Which one do you want to do? Potassium. Does somebody want to come up and do it? Nope. What's the symbol for potassium? K. Yes, all my K's look lowercase. I've never been able to write a capital K in my life. Okay, I had a capital K for potassium. Okay, so potassium is there. Wow, we could have saved a whole bunch of work if I hadn't erased that. Okay, so what is first? 1s2, 2s2, 2p6, 3s2,
3p6.
3p6, Then,
One.
how does everyone not know, and then everyone knows at the exact same instant? That was weird.
Is that one?
4S1.
Is it two?
Four
Would it be
S1.
one? 4S1?
Yes.
Just stick to it for them.
4S1. Potassium has 1 in the 4S. Okay? So what can we make easy from potassium? Zinc. Okay? What do we have to do to turn potassium into zinc?
That's 2.
4S1 becomes 4S2, 3D10. The count is going to be 10. So there is zinc.
It's wrong.
What's wrong?
You got a K in the front. It's supposed to be Z.
Ah, there you go. There you go. Zinc. 100% on the quiz. It was 3/4, 75% on a quiz, and a little question mark. Why did you put K? Does anyone want to do the rest? Any of the other ones? Which one? 6. Mercury. Hg. So change that for Hg before we do anything. Okay. Mercury. How's it going?
Oh,
Mercury. Oh. Okay. Rather than write it down, let's just do it verbally. Okay. So we're at here at zinc. We're at 3D10. What's next? 4P6. These are P's. They're in 4. So 4P6, and then 5S2, then 4D10, then 5P6, then 6S2, and now this is so far down that we have the F that I said you would never have to do in homework or anything, okay? But this is up here, so might as well do it, okay? Remember, the F's are set back 2 numbers, okay? So this is, it's in row 6, so it's a 4F, and there are 14 of them. So that's a 4F14 there. Then we're on 5D10. Okay? Big.
Is this one mostly on the test?
No, it has its F, so
Can I
if,
just
it-
process
if,
it
if, you, if it's on the exam, you bring it up to me and you say, I'm not doing it. Right? But, yes, it's long, and yes, it's longer than you'd have to do because it has F's. But, hoping on the next slide, we make this even simpler and shorter than the electron configuration. It's noble gas notation, okay? So, what we've been doing is we take one, and we pick one that was further down, and we'd add to it. And we'd add to it, and we'd add to it, right? What noble gas notation does is it picks a noble gas and says, we're starting here, and then what is on top of that, okay? So, for zinc, we would say argon, and then you put argon, you put zinc, and then we say argon in parentheses. That means whatever argon is, this denotes that that we're putting it there. We're saying that we're starting at argon, okay? And then we go, what's on top of that? What is on top of the argon? What's the orbital after or argon? So, yeah, so we have argon, then 4s2, and then what is zinc? 3d10. So that is how you do zinc in noble gas notation. So you avoid writing all this junk. That's the first stuff that nobody even cares about, right? It's so buried in the electron cloud, it doesn't do anything. So we don't care about it. So we write, this is symbol for zinc, then we're saying we're starting at argon, and then this is on top of the argon. So, you can take this and expand it back out if you wanted to, right? You would just figure what is the electron configuration of argon and stick it in there. Okay. So, like this is showing, iron, first part is the same as argon. So you cut that out and just say argon and leave 4s2, 3d6. It's just what we did. Iron is here, our zinc is here.
Oh, so we're looking at, the slide beforehand where you have the Br and the zinc. One of them's 35 and the other one's 30, so if you're trying to do it like activity, electron configurations, yeah, so if you're looking at 4 and 5, 4 has 35 and 5 has 30, so you could do that one like that, correct?
Right. So both bromine and zinc would use argon. Okay. Anything in this period, this row, not that, it's in anything in this row, it would start with krypton, and then 5 S's, and then 5 S2, and 3D10, and then 5P, whatever.
Well, you always start with a noble gas.
Always start with a noble gas. You can't say, I'm starting at manganese and then doing 3D 1, 2, 3, 4, 5, 6 on top. You always have to start at a noble gas. Yeah. Yeah.
What was the practical application for this?
It saves you from writing all that junk out.
I know, but why are we doing it in the first place? I mean, it's just to find the charge, or like I missed it.
Where this is going to come in useful, thank you for asking. What really matters is what is in the outer shell. Okay? And so, yes, we could just teach you how to figure what's in the outer shell. But then the question becomes, well, then what's under it? So then you might as well do all of it. Okay? The outer shell is going to be the S's and the P's, and we'll talk about that. Okay. Valence electrons are the main group element. So valence electrons are the ones on the outside. Okay. The valence electrons are in the last filled principal energy level. That, yes, that sounds horrible, confusing. Forget the whole definition if you want. We can use your periodic table as a shortcut here. Okay. Valence electrons occupy orbitals in the valence level. Okay. The valence level is the highest number. If you wrote this all out, okay, pick the highest number. So in this one, it went 4s2, 3d10. 4 was our highest number. Okay. So then you say how many electrons were in a 4? In this case, it was 2. Okay. The easier way to do this is up here. Okay. You can have up to 8 valence electrons. Valence electrons are always in S or P. So you count 1, 2, 3, 4, 5, 6, 7, 8. All you have to do. How many valence electrons does phosphorus have? 5. 1, 2, 3, 4, 5. Okay. How about fluorine? 7. How about sodium? 1. That's how you count valence electrons. Okay. You get down here, you skip these. So bromine has 1, 2, 3, 4, 5, 6, 7.
Why do you skip them?
Remember, maybe I didn't say it. We were saying that these are a lower number, right? The D's are set back one number.
Mm-hmm.
What that means is that they're actually in the electron cloud for the 3 D's is actually further in than the 4 S's and the 4 P's.
So is that why you're saying to count these instead of looking at this? Because if you have a D on this, it's still smaller than...
Right. So on this, you can't just go at the end. You have to say 4 is higher than the 3. So these 10 in this D don't make a difference.
Okay.
You just use 2 and 4. I use the periodic table. Okay. Just like I said, Einstein counts 1, 2, 3, 4, 5, 6, 7. okay? Don't worry about getting a periodic table and counting, nobody's gonna laugh. Okay. How many valence bromine? How many valence electrons are in bromine? 7. Okay. Do it up here. 1, 2, 3, 4, 5, 6, 7. Or you can say, what's the highest number up here? 4. How many are in a 4 up here? 2 and 5 and 7. Whichever way works easier for you. To me, this is a whole lot easier. How many valence electrons in fluorine? 7. Lithium?
1,
1. Sodium?
1,
1. Carbon? 4. Silicon? 4. Lead? 4. So you know it goes by group, right? Everything in this group has 1, everything here has 2, 3, 4, 5, 6, 7, 8. And remember we were talking about when it forms ions, it wants to get the 8 valence electrons. So fluorine has 7, so it's here. If it gains 1, it can move over. Go ahead and think about that. Don't text yet. I didn't activate this. I'm trying to bring it back. Does everybody already have the answer? How many does it have?
2.
Forget technology for today.
so it was 3.
Yeah, why is it 2 and not 3? I had 3.
Here's titanium. Titanium is here. Okay.
Oh, I
So,
was looking at 81.
That's 81. Oh,
Yeah.
that's TSTL, yeah. Tellurium. Okay.
Okay.
But TL would have 3, right?
Right.
Okay.
So you skip these.
Oh,
So
yeah,
TI,
yes,
yes. TI has 1, 2, then you skip these. These don't matter. Tellurium would have 1, 2, 3.
Okay. That was technically right.
Okay. You can do the same electron configuration for ions with atoms. It's just as easy, but you have to do just a touch of thinking before you can write it out. Okay? So, all you have to do is think of the electron configuration for the atom, and then either add or subtract the electrons that you have to add or subtract to make that ion. So, electron configuration for sodium. Okay? If you were going to write it for sodium, what would the last little thing that you wrote be? 3s1 would be the last thing you wrote. When sodium forms an ion, what happens to its electrons? Does it gain or lose? It loses. How many does it lose? It loses 1. So you basically erase that 4s1 and you fall back to neon. So then the last thing you would write would be two P6. Okay. So here is our 2P6.
Explain that again.
Hmm?
Explain that again.
Yeah. So, we're dealing with sodium. So I would start and say, what is the electron configuration for sodium? So sodium is what?
1s2, 2s2, 2p7.
2P6, 3S1, correct? Yes. So then we said, okay, this is a sodium atom before it forms an ion. And then we said sodium loses one electron because it is here, so it wants to go back one to get the neon, noble gas. So it loses one, so we erase the last electron up here. And so that
Oh, okay.
becomes the electron configuration for the sodium ion.
Now, per se, it wasn't 3s1 that you took off, it was 3s2. Would you just subtract 1 from that?
Where-
Or would you take the whole entire thing off?
So, if it was 3s2, it wouldn't be sodium, it would be magnesium. So let's do that. So if we have a magnesium atom, you would have 3s2. What happens to the electron in magnesium when it forms an ion?
Oh, it loses 2, so
It
you still take the whole
loses
thing
two.
off.
Right. Remember, you're trying to get to the noble gas configuration. And our neon is this. So you're going to erase anything here, whether it be the 3 S's or the first couple 3 P's. It would all fall back to come to this.
But that would only be if it was magnesium 2 plus.
Right. Magnesium, anything in this group, this column, will always form a 2 plus. Okay?
But yeah, as it's drawn before, it's not.
Oh, yep, thank you. 2 plus.
Makes sense.
Makes sense. Good question?
Yeah, so if you had, say you had a question ask you for sodium, ion, and noble gas notation, could you just write no? Down the end of it?
If you really want to, yeah, the question wouldn't ask for that, but if it did, it would be sodium ion is neon. Okay? Before we do that, let's do another one. So let's do one that goes the other way. Okay? So let's do oxygen. Okay? So I'm going to write oxygen. What's first? 1s2,
2s2,
2s2, 2p4. Oxygen forms an ion. What happens?
3-1.
It's going to gain how many? 2. It wants to get to a noble gas, so it goes 1, 2. So we add 2 electrons to here. If we add 2 electrons, what do we do? How do we write that?
2p6.
Change 4 to a 6. 2 minus. And so now, again, we have neon, right? That's neon. It's a noble gas. Okay. This is a really simple little thing. Okay. Lewis symbols are going to get a lot more complicated in a month or so. Today, they're incredibly simple. Okay. All you do is you figure out how many valence electrons an atom has, or an ion, and you put that many dots around it. Okay? So, lithium. How many valence electrons does lithium have? 1. So I'm going to put Li, and then I'm going to put 1 dot that represents its one valence
Doesn't matter what side you
electron.
put anything on?
Hmm?
Doesn't matter what side you put them on?
No.
They have it on the other
They
side.
put it on the other side. We'll see. It doesn't matter where the first one goes. Just like the arrows, it doesn't matter where the first one goes as long as you follow the directions after it. Okay. So lithium, if we add 1 more, we get lithium to beryllium. Okay. And so beryllium has the 1, and the second one goes opposite it. Okay. And then we go to boron, and then I would do, we already have 2 here, and then you can put a third one on top or bottom, it doesn't matter. For some reason, they all kind of shifted it. I don't know, it doesn't matter to me. Okay? And then the fourth one, carbon, now you have 4, you can put 1 there. Just like arrows, you don't want to pair them until you have to. Yeah.
Did you start at like the top, like plug up dot at the top?
Yep.
And then just go clockwise? Track line?
No.
Why has to be follow the same like side?
The second one has to go opposite the first one. So if the first one goes on the top, the second one has to go on the bottom. Okay. Then you have carbon. After carbon, you go to nitrogen. Now you have 5, so now you can pair 1. And then after that, you would pair the opposite one, and then go in the same order again. Okay?
So, you said you have to pair the opposite ones so they're directly across, but on this example, it pairs the adjacent with the current.
Yes, it does.
Not
You can't use on the end.
I don't care.
Okay.
I'll be completely honest with you. This is not going to be on a quiz, and I'm pretty sure it's not on the final. Okay? Like I said, the Lewis dots are going to get, if anyone has taken chemistry before, you know they're going to get a lot more complicated. Okay? So if you don't get this now, you're going to come back to it. Okay? So basically, based on what they're doing, it appears the rules are the second one goes opposite the first one, and then don't pair until you have to. Okay?
And you can't have any more than 8, correct?
You can't have more than 8, because then it's no longer valence electrons. You only have 8 valence electrons.
So if you have 9, you just make another shell? Or you just
If
have
you
10?
had, you wouldn't have
Oh,
one.
there's
that
only
had.
8 across, okay.
So, because as you go from left to right, you add valence electrons, that's why we have this periodic tendency. Okay? Everything here has 1. If you have 1, you behave like you have 1. Everything here has 2. If you have 2, you behave like you have 2, and so on. Okay? In general, there are these periodic properties that we call them. And a couple of them are relative reactivity, ionization energy, and atomic radii. I believe they all have their own slide there. Yeah. So, here is our periodic properties going down a group. Okay? As you go down, things become more reactive. Okay? So here's lithium in water, it's not doing anything. There's sodium, I said potassium is worse, and there's rubidium, and there's cesium. Okay? You can see it getting more reactive, right? So you just have to remember, as you go down, you get more reactive. Ionization energy is how much energy it takes to remove 1 electron. Okay? To me, the name of this term is a little bit confusing. Okay? Because fluorine, when it ionizes, it gains 1, right? But ionization energy refers to how much energy it takes to remove 1. So if you know that fluorine likes to gain 1, do you think it's going to take a lot of energy or a little bit of energy to remove 1? A lot, right? Lithium likes to lose 1, so it's not going to take much. It wants to give it away anyways, right? So do you think ionization energy goes higher or lower as you go from left to right? higher. These like to lose them, these don't. So as you go left to right, ionization energy goes up. Okay? Don't worry about this. What this is showing is magnesium losing one electron takes 738 kilojoules per mole. You don't know what a mole is yet. Okay? Atoms that have a low ionization energy, give them up easily because they're not holding on to them very tightly. They don't really want them to begin with, so it's easy to steal them away. Okay, so here is our trend again. As you go from left to right, ionization energy goes up. As you go from the bottom to the top, it goes up. So the way to remember this, the way I do it, is which corner is the highest? Helium, top right. If you can remember that, you can figure it out, right? If the top right is the highest, that means the right is higher than the left. And if the top right is the highest, that means the top is higher than the bottom, right? So to remember the trends, all you have to do is remember which one is the highest. Which has higher ionization energy? Magnesium or calcium? Magnesium. Oxygen or fluorine? Fluorine. Sulfur or fluorine? Fluorine. Fluorine is both further to the right and further up. Okay? It would be a trick question, not something you couldn't answer if it said sulfur and nitrogen. Nitrogen is higher, but it's further to the left. Which one is it? That you would not be asked that question. Okay? Either they're going to be in the same row, the same column, or they're both going to be trends in the same direction to make it really easy for you. Atomic radii are the size of an atom. Okay? So the way we measure this is if you take two atoms, okay, we can measure the distance between the nuclei between those two atoms. So this is chlorine bonded to chlorine. Okay? Chlorine is a halogen, which means it's one of those diatomic molecules. Remember? So you gotta have two, which is why it's chlorine to chlorine. Okay? I don't know how they do it, but somehow they have a way of measuring the distance between that chlorine nucleus and that one. Okay? If you can do that, that is the distance of two radii. Remember the radius is the distance from the center of a circle to the outside, right? So that is the radius. Okay? So here we have one radius and two radii, right? So if you can measure that distance, take half of that, and you have the radius of one atom. Okay? You're not going to have to measure the radius of an atom, right? So what you have to remember are these trends. Okay? So going from left to right, you get smaller. Going from top to bottom, you get bigger. So which corner is the largest?
The bottom left.
Bottom left, which makes the top right the smallest. Whichever one you want to remember, that's how I would remember it. Either remember francium is the biggest, or remember helium is the smallest. They'll both work the same way when you try to figure what a trend out. So here we see actual relative sizes. There's helium, tiny little thing. There's francium, it's the biggest one. Okay. What is bigger, magnesium or calcium? Calcium? Oxygen or fluorine? Oxygen, sulfur or fluorine? Sulfur. Got the trends? is going to have to memorize them. There are underlying principles that dictate that, but I think it would just confuse you beyond all heck. If you're really curious, let me know and I can explain it to you. People are putting everything away. Is this the last slide?
Yeah.
See, that was an observation and then a hypothesis, and I tested that hypothesis by asking. Okay? So I think the law is students want to go home.